Welcome to Math with Professor V. In this video, we're going to go over applications of differentiation, in particular, finding maximum and minimum values, how to find the absolute or global extrema of a function using the extreme value theorem. Lots of good stuff, but I'm going to break it all down for you from the beginning. So, to start our discussion, we want to look at one of the most common applications of derivatives, and that is optimization. In these problems, we're going to try to find the best solutions. What do we mean by best? Well, it could be the max profit of something, the largest volume, perhaps the minimum cost, or the smallest amount of materials needed. We're going to be getting into that later. So first, we have to begin our discussion by considering what do we mean exactly when we talk about the max or min value of a function. So I want to motivate the discussion graphically. I want you to look at the graph right here of some function and identify what the maximum and minimum values are, just visually. So if we're looking here, the highest point on the graph occurs when x is -1, and the function value or the y value is, let's see, 1, 2, 3, 4, 5. 5. So you could say the max occurs at -1, so I could say f of -1 yields me the max of 5. That's a very thorough answer because now I know -1, 5 is where the max is. Similarly, can you identify where there's a min? Just visually look, oh yeah, right here. And that occurs when x is equal to +1 and y is 1, 2, -3. So f of 1, -3. Okay, now we're going to be a little bit more specific about what kinds of max or min we're looking at in the following. So definition, let C be a number in the domain D of a function f. Then we say f of C is the absolute maximum value of f on D if for all x in the domain D, f of C is greater than or equal to f of x. So it's the largest y value, or you could have others that are equal to it, but nothing larger than it in the domain of a function. The largest function value. That's the absolute max. And then similarly, we say f of C is the absolute minimum value of f on D if for all x in D, f of C is less than or equal to f of x, okay? So as a note, absolute maxima can also be called absolute extrema. We use that expression as well, that terminology, or you might hear global extrema, it's all the same, depending on like your textbook and your instructor, okay? Good. Now, we talked about absolute extrema. What about local extrema? That's something else that we're often interested in. So again, here's another little graph to motivate this idea. I want you to consider the behavior of the function near the x values labeled on the graph. Let's go in order from left to right. So starting right here, where x is equal to a. Look at the function at that point. Look at the function at that point. Well, f of a is the lowest, right, or the smallest value, smallest y value in some little neighborhood, meaning the graph exists on the left and right of a. So we identify that or can classify it as a local min. Relative min is another word you'll hear. Okay, what about moving on, f of b? F of b is right here. That's f of b. Well, that looks like the highest value in some little neighborhood. That's the highest value. These mean ditto for what's up above, so you don't have to rewrite it. So then we call that a local max. All right, moving on. don't forget about little f of 0. What does f of 0 look like? That looks like the lowest value in a neighborhood, and it looks like the lowest value of the entire graph. Oh my goodness, right? Because this just keeps going up. This keeps going up. I have no reason to believe otherwise. So f of 0 is special. F of 0 is a local min, and if it's the smallest for the entire graph, for the entire domain, it's the absolute min. Ooh, so it could be more than one thing. Cool. What about next, f of c? Here's f of c. What does that look like to you? There's a neighborhood of points around it that are smaller. So f of c is the highest value in some little neighborhood. So yep, that makes it a local max. And then who's left? Oh, right here. F of d. F of d is, it's barely smaller than everybody else, but it is. It's the lowest value in some little neighborhood. So it is another local min. Okay, so here's some important things to notice. You can have more than one local min. You can have more than one local max. A local min can also be an absolute min. Also, there is no absolute max. And that's because, notice here, this graph, there's arrows on the endpoints, so we're going to assume that it just continues upward forever. So there is no y value or function value that's larger than all the rest, since this graph just goes up, up, up forever. Okay? All right, so now let's put some definitions formally to tighten up what we mean by this neighborhood situation. Okay, that's a little loosey-goosey. Let's make it nice and crisp. So definition, we say that the number f of c, so that's the y value, f of c, we call it a local maximum value of f if f of c is greater than or equal to f of x for all x that are near c. And then similarly, f of c is the local minimum value of f if f of c is less than or equal to f of x for all x near c. And as a note, when I write near in quotes like that, near c means in some open interval, some neighborhood, right, containing c. So notice here, all of these local extrema, the local min, the local max, the local max, the local min, there were points on the graph to their left and right. That's what we mean by there's some open interval containing them. Look, here's a local max. There's points to the left, points to the right. There's an open interval or a neighborhood containing this point. That means you can't have a local max or a local min be the end point of a graph. So we looked at a graph earlier just a second ago. See how this has endpoints? This can't be a local min, no, because there's no points to its left. There's no open interval or neighborhood around this point. This also cannot be a local max because it is an endpoint. Okay, so local mins and local maxes cannot be endpoints. All right, I'm glad we got that straight, you know. I had another note for you guys. Yeah, believe it or not. So, local extrema. When we say extrema, that's like the generic term, meaning it could be min or max when you just say extrema. So these are also sometimes referred to or called relative extrema. Okay. Are we getting confused with the vocab? Maybe a wee bit. Okay. So local or relative Those are kind of interchangeable. And then you have absolute, and then some people call that global, okay? And then when you want to say min or max, then you can say extrema. That's the plural. Extremum is just one, okay? Good. Hopefully that vocab lesson helped. Now, you should also be aware that a function's extreme values may occur at multiple locations. So let me give you an example. Say we have, what's a function that we all know and love very well? How about f of x equals sine x? Do you love it? Can you graph for me like a period or two? Yeah. So remember, sine of x has amplitude 1, period is 2 pi. Is that straight? No, that's crooked. Hold on. Bear with. There we go. Okay, here's my x-axis. Here's my y-axis. It's going to go up to 1, down to -1. This is pi over 2, pi, 3 pi over 2, 2 pi. And then here, this is going to be 5 pi over 2, 3 pi, 7 pi over 2, 4 pi. Look at me. I'm going to do 2 periods. Why not? Sine starts at 0, up, back to 0, down. 0, up, back to 0, down. Et voila. Do you need to review how to graph sine? It's okay. Don't feel badly. I have video lectures for pre-calc and trig, so just hop on over there if you just need a little refreshing moment. Okay? Refresh. Just graphically, visually, tell me, is there a local max? Oh yeah, the local max, I see it. Here's one, here's another one, and I only graphed 2 periods, but had I kept going, there would have been more this way. There's more that away. So how would you write out your answer? Whew. Okay, so local max. When they ask you for the local max value, they want the function value. They want the y value. So the local max is 1. And it occurs at infinitely many places. I can't sit here and list them all out. I'm going to say it occurs at x equals. The first one is pi over 2. And then it repeats every period, right? So every 2 pi added to that, like this right here would be pi over 2 plus 2 pi, so 5 pi over 2. And then keep going and going and going. So I'm going to say pi over 2 plus 2 pi k, where k is an integer. Or you could say k is an element of the set of integers. That way you don't have to write all that out. You know, that means k is an integer. All right. That's the local max. What about local min? Do we have a local min? Oh yeah. Again, infinitely many of them. Here, here, etc. So the local min is -1, and it occurs at x equals, well, this is 3 pi over 2, isn't it? X equals 3 pi over 2 plus 2 pi k, where k is an integer. All right. All right. It's also important to note all these local maxima are absolute maxima, right? The function never achieves a value higher than that. And the local minima are also absolute minima. Okay, let's make a note of that. Both of these are also absolute. So they don't have to be unique. That's the point I wanted to make, is that when you have an absolute max, it can occur in more than one place. Same thing for a local max. So don't feel like it just has to be one and done, okay? Now, we just looked at a function that had infinitely many local and absolute extrema, right? There's infinitely many here. We also have some functions that have neither. They don't have a local or an absolute or global extrema. Let me give you an example, and it's not some weird function. It's one that, you know, you probably are pretty fond of. How about f of x equals x cubed? That wiggly guy. I know. So just a rough sketch. No, don't stress out. We're just gonna do a very rough little sketch. X-axis, y-axis. Boom. Here's x cubed. Oh, is there a local min or local max? No. No, there is no point where there's a neighborhood of points around it that are all smaller or all larger. Is there an absolute or global max or min? No, it goes up and down forever. So there's no local or global. Remember, local is the same as relative. Global is the same as absolute. Extrema. Okay, so this is interesting because how do we know, or how can we be guaranteed that a function is going to have absolute extreme values? Well, you are in luck. We have the extreme value theorem. Here we go. If f is continuous on a closed interval from a to b, then f attains an absolute max value f of c and an absolute min value f of d at some numbers c and d in the interval from a to b. Bam, you get both an absolute min and an absolute max from the extreme value theorem. But did you notice there's two conditions that your function needs to satisfy? Yes, it requires that your function be continuous and that we have a closed interval. Oh, we're going to investigate that. Don't you worry. A closed interval. Closed interval, did you notice they wrote it out? It's from A to B, so we have to include both endpoints. Okay? So I'm going to show you an example where we kind of play around with the conditions and you can see how the extreme value theorem will hold and fail depending on if I satisfy or don't both of these conditions here. So let's just do like a nice relaxing little example. Let's look at f of x equals 1 over x. Okay, now right off the bat, f of x, we know its domain is all real numbers except for x equaling 0. And we have a theorem that you learned early in Calc 1, hopefully you remember, that all rational functions are continuous on their domain. So as long as the interval that we're looking at does not include 0, this function is continuous. So we can say it's continuous if x is not 0. Okay, I'm just going to study values and intervals that are positive for x. So we just need to graph the first quadrant. Our investigation is going to be mostly between 0 and 5. How's that sound? Oh, good. I'm glad you're excited. Okay, so we don't need to scale our axes the same, you know. Sometimes students stress about that. Let's do what's comfortable for us. That's really what matters. 1, 2, 3, 4, 5. This is 5, okay? But then this guy, this is 1. And then this is a half. And then this is like 0.25, okay, 1/4. So let me get graphing. Here we go. So it goes through 1, 1. This is 2. F of 2 would be 1/2, so that's right here. F of 3 would be 1/3. F of 4 is 1/4. F of 5 is like 0.2, 1/5. So something like this, okay, more or less. Okay, beautiful. All right, here we go. So I want you to tell me if we have absolute extrema on the following intervals for our function. So f of x is 1 over x, and I want you to look on the interval from 0 to 5. So notice this is open. This is an open interval. It's not closed. Not closed interval. Now, it's fine. This function is continuous on this interval because it's continuous so long as x doesn't equal 0, and I'm not including 0. So on the interval from 0 to 5, do we have an absolute max? No, because at 0, the function's not defined and it goes up, 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 up forever. And you could always find some y value larger than whatever you say would maybe be. the absolute max. Like if you pick some y value over here that's all the way up there, someone can get just a wee bit closer to x equals 0 and get an even higher function value. So forget that. And then same thing here, we're not including 5. So there is no absolute min because you can't actually say f of 5. The interval's open. So say you were like, oh, well, 4.9, f of 4.9 is my absolute min. But then someone could just come up next to you and say, well, how about 4.99? That function value is smaller. Well, how about 4.999? How about 4.9? You know, this game will never end. So no, there's no absolute extrema. Sorry. All right. Well, I'm not surprised. We didn't satisfy the conditions of the extreme value theorem. We needed continuity. We had that, but we didn't have a closed interval. Shame on us. So we shouldn't be surprised. Okay, so now we're going to still look at f of x is 1 over x. How about on the interval from 0 to 5? Okay, this time I made a closed interval. I can say, yes, I can say that f of 5 is my absolute min. Do I have an absolute max? I'm including 0 this time. Well, no, f of 0 is undefined. Remember, we have a vertical asymptote here. So there's no absolute max. Are we surprised? No, we violated one of the conditions of the extreme value theorem because this function is not continuous at x equals 0, and x equals 0 is part of the interval. So I'm not surprised there. Okay, here's our last chance. I need both an absolute max and an absolute min. Let's come up with an interval that satisfies both conditions. The function has to be continuous on the interval, and it has to be a closed interval. So don't include 0 and just make it closed. Lots of different options. How about we just go from 1 to 5? How's that sound? Now we get both. Now we get an absolute max and we get an absolute min. So f of 5 is still my absolute min. Do I have an absolute max? Yes, f of 1. Because we're only looking at this portion of the graph between 1 and 5, inclusive. So I could say, oh yeah, f of 1 is my absolute max. Extreme value theorem guarantees we get both an absolute max and an absolute min, but we have to meet both conditions. The function has to be continuous on the interval and it has to be a closed interval, okay? Woo! So now we know, all right, if we have a function, it's continuous on this closed interval, we've got our absolute max and our absolute min. But how do we find them? Most of the time, you're not going to be given some graph and they go, hey, look at it, figure out where the extrema are. So let's kind of analyze what we can do, what calculus tools we can do and use to identify them, okay? Remember that first little example I showed you where the graph didn't continue forever, but just looking, we identified where the local max and min were. This was at the very beginning of the lesson. F of -1 was 5. We said that was our local max. And then f of 1 is -3. That was a local min. You remember doing that? And I want you to notice something very special about these two places on the graph. If I were to draw a tangent line, that looks horrible. Excuse me. I was too excited to drive this point home. Here's my tangent line at the local max. Here's another tangent line at the local min. What is the slope of the tangent lines at each of these points? It's 0, right? The slope is 0. The slope is 0. So observe, a max or a min, doesn't matter, may occur when the tangent line is horizontal. Yes, bingo. Horizontal. Horizontal tangent line means f prime of x is equal to 0. All right, so this takes us to Fermat's theorem, one of them. He has another one, don't worry. If f has a local maximum or local minimum at C, and f prime of C exists, then f prime of C equals 0. So basically what that's saying is, if your function has a max or a min and the derivative is defined there, it exists, then we know that the derivative is equal to 0. So if we were to basically reverse engineer this, I give you a function, right? I give you f of x. If you're just given some function, what's the process? You take f prime of x, you take the derivative, okay? Set it equal to 0, and solve. And those will give you places where you have potential local extrema. So this leads us to believe we can find local extrema by the first part of the process is finding where f prime of C is equal to 0. Now, this will give us or start us on the path to finding some of the extrema, but not all. Because remember, this theorem required that f prime of C exists. Namely, that the function is differentiable at that point. But what if it doesn't? We have looked at many cases where functions aren't differentiable at points, but they are continuous there, and you could have a local min or a local max. Let me show you an example, okay? What's a very famous function that has a point where it's not differentiable? Absolute value of x. Do you remember what the shape of it looks like? V shape, right? Good, good, good. Okay. Absolute value of x. This is crude little graph, but it will get the job done. So absolute value of x is not differentiable at x equals 0, right? F of x is not, this is a nice abbreviation for differentiable at x equals 0. Remember, any sharp points on your graph, cusps, are where your function's not differentiable. Because if you look at the slope of the tangent line from the left, it's not equal to the slope of the tangent line from the right. Okay, so f of x is not differentiable at x equals 0, but I want you to notice something. F of 0 is a local min. Not only that, it's also an absolute min. Uh-oh. F of 0 is a local and absolute min. So if we were to try to take the derivative, set it equal to 0, we wouldn't get the point x equals 0. Okay, that's upsetting, mildly upsetting. And one more thing, just because the derivative is 0, it doesn't guarantee that we have an extreme value, a local min or a max. I want you to think back to f of x equals x cubed. Remember what that guy looked like? We just graphed him. You're like, of course, Professor V. How could I have forgotten? I'm not that girl from 50 First Dates. Do you guys know that movie? Drew Barrymore, Adam Sandler. It made me sad. Okay, here's x cubed. F prime of x, 3x squared. If I set it equal to 0 and solve, I get x equals 0. And it's true. F prime at 0 is 0. But do I have a local min or a local max there? The derivative is 0 there. No, it's not a local min or a local max. Uh-oh. So that's not good enough. F of 0 is not a local min or max. So before you get too upset, we have in the following lessons a way to identify where your local extrema are. And you have two different tests. You could do the first derivative test or second derivative test. That's not going to get covered in this video. We're just going to focus on absolute, okay? But it is important that you appreciate that where the derivative is 0 and where the derivative doesn't exist contain all of the possible places where we have local extrema, okay? And that's basically where we begin our search. Just think of it like you're on this hunt to find the extrema in this unit. So these points are all important. We're going to give you more criteria coming soon. We don't want to overwhelm you guys right now. And all of these places where the derivative is 0 or doesn't exist are so important, they are critical. And so we call them critical numbers. A critical number of f is a number c. Now be careful, it has to be in the domain D of the function such that either f prime of c is 0 or f prime of c does not exist. Okay, all of those places are called critical numbers. As a note of caution, please be careful. A critical number must be in the domain. Okay. And the values still may be of interest even if they're not in the domain. We'll discuss what to do with them later. So let's try finding some critical numbers right now for a few functions, and then we'll get into our discussion again about absolute extrema. So say you have f of x equals the square root of x, and I ask you find the critical numbers of this function. The very first thing you should do is list the domain. And that's not going to be part of the directions, but that's just what you need to do. So the domain for square root of x we know is from 0 to infinity, no negative numbers. So let's take the derivative. If you want to remind yourself, this is x to the 1/2. So f prime of x is going to be 1/2 x to the negative 1/2, which is the same as 1 over 2 square root of x. Yes? Okay, so critical numbers come from two places. First place is where f prime of x is 0. And the second place is where f prime of x does not exist. And here's just the easiest way to do it. When your derivative is a fraction, basically. One term, the derivative is equal to 0 when the numerator is 0, and the derivative doesn't exist if the denominator is 0. So f prime of x equals 0, that means the numerator, which is 1, would equal 0. Well, that doesn't happen, so none. And then the derivative doesn't exist, that would mean the denominator, 2 rad x equals 0. That happens when x equals 0. Now, is x equals 0 part of the domain? Yes, my domain originally includes 0, goes up to positive infinity. So I can say that x equals 0 is a critical number. That's a critical number. And then sometimes you're asked for critical points. Well, then they want an actual ordered pair, an x comma y. And to get that y value, you always go back to the original function. It's a point on the graph. It's a point on f of x. So f of 0, which is 0, right, is the y value, corresponds. And you could say 0, 0 is a critical point. Good? Now, I had one more example to show you, and I wrote way too large. So we're just going to shrink this little sucker. Okay. And example 2. I'll zoom. Don't worry, I got you. Here's another function. F of x equals 1 over x. Again, I want you to find the critical numbers, okay? What's the domain of this function? Everybody except 0, right? All x's such that x cannot be 0. So let's find the derivative. If you want to remind yourself, this is x to the negative first. So f prime of x would be negative x to the negative second, which is negative 1 over x squared. So again, critical numbers, we want to check where does f prime of x equal 0 and where does f prime of x not exist. The derivative is 0 where the numerator is 0. That never happens. The derivative doesn't exist when the denominator is 0. That happens when x is 0. But this time, x equals 0 is not in the domain. So what would you say? You would say there's no critical numbers. Okay, because it's not in the domain. Yeah. Yeah. It's not like you're going to skip over 0 or not pay attention to it. There's a vertical asymptote going on there. So you still have to investigate it. It's important when drawing the graph or considering extrema, but it's not a critical number, okay? Let's practice now a few more examples where we're going to be finding critical numbers. Let's look at the function f of x equals natural log of x over x squared. You guys, it's essential. We got to write the domain first, okay? Now, when you have natural log, remember the argument has to be greater than 0, strictly greater than 0. And this means x can't be 0. So overall, the domain for this function is from 0 to infinity. That takes care of x not equaling 0 from the denominator, and then natural log is defined on that interval. Perfect. Okay, so let's go ahead, take the derivative, see where it's 0, and see where it doesn't exist. We have to do the quotient rule, right? Do you sing that little song, low d high minus high d low over low low? If you don't know it, I'll link it here. Okay, f prime of x is denominator times derivative of the numerator, so derivative of ln of x is 1 over x, minus numerator, high d low, times derivative of the denominator, that's 2x, over denominator squared, that's x to the 4th. Okay, so let's clean this up. X squared times 1 over x, that's just going to be x minus, let me rewrite this as 2x ln of x over x to the 4th. And then you guys see, I can cancel out 1x from everybody. So let's simplify. That means f prime of x is going to be 1 minus 2 ln of x over x cubed. Yeah? Are you good? Okay. So critical numbers come from two places. First place is where f prime of x equals 0. This happens when the numerator is 0. So just look at the top. Set it equal to 0. 1 minus 2 ln of x equals 0. That means ln of x equals 1/2. You good? Then just rewrite this in exponential form, or take e and raise it to both sides. So x equals e to the 1/2, which is square root of e. Okay, and the problem just asked for critical numbers. So here's 1. Is it in the domain? Yeah, square root of e is between 0 and infinity, so we're good. Okay. Second place where we get critical numbers is where the derivative does not exist. And that happens when the denominator is 0. The denominator is x cubed, which only happens if x is 0. But that's not in the domain. Remember, the domain goes from 0 to infinity, not including 0. So it's not a critical number. Nope. Sorry. So we do have one critical number. Critical number x equals square root of e. What if your instructor asks for the critical point? The critical point, then you need to take the critical number and plug it into the original, always into the OG, okay? So let's do that. So f of the square root of e is ln square root of e over square root of e squared is just going to be e. Ln square root of e, or ln of e to the 1/2 is just 1/2 over e. So this is 1 over 2e. Ooh, okay. So the critical point, maybe they want that, you know, you don't want to be a one-trick pony. You want to give them a critical number if they want it, give them a critical point if they want it, make everybody happy. Rad e, and then 1 over 2e. How do you feel about that? Yeah, it's good. I mean, there's so much going on in this lesson. If you feel slightly overwhelmed, it's okay. It's okay. It's just going to come together the more you practice, and you got to delve deeper. Think of it like this. You know when you put a puzzle together in the beginning, it looks like a hot mess? And you can't see the picture, but you're just like putting pieces. Usually I start with the border. You know, I do the corners and then the edges. And then as you fill it in, you're like, oh, okay. So that's how this unit's going to go too, okay? Just hang in there. All right, let's recap. So by our reasoning so far, we can say that if f has a local extreme value at c, then c is a critical number and f prime of c, oh, that looks ugly. Hold on. Let's fix that. F prime of c is 0, or that's it. F prime of c doesn't exist. Okay, but remember in the very beginning we were talking about absolute extrema, and we want to know where these absolute max and min values occur. So consider the function graphed below. I hope you can see it. Oh me, oh my. Here it is. Can you see it now? Yes, Professor V, we see it. Okay, fabulous. So consider that function. It's f of x equals 2x minus 2. And we're just looking at a piece of it. We're looking at the piece that's on the interval from -1/2 to 2. Now you remember our extreme value theorem? Yeah, our extreme value theorem, let's abbreviate. Who wants to write extreme value theorem? Not me. The EVT guarantees us what? Both an absolute max and absolute min, so long as we have a closed interval and our function is continuous on that closed interval. Do we have those here? Yeah, because look at this interval. It's from -1/2 to 2. It's closed. Is our function continuous? Our function is sweet little 2x minus 2, a line. Lines are boring polynomials, but they are polynomials. Those are continuous on all real numbers. So both conditions of the extreme value theorem are satisfied. Do we have an absolute max and absolute min? Just look at this little graph here, this little line segment. Yeah, I mean, right here, this is my absolute max. So f of 2, which is 2, that's the absolute max. And then down here, there's my absolute min. Who's that? That's f of -1/2, right? That's -3, that's the absolute min. Okay, cool. But is the derivative 0 at those points? No, right? Well, what's my function again? My function is 2x minus 2. Take the derivative, f prime of x. It's just 2. That's never 0. That means this function has no critical values, actually, right? Because it's never, the derivative is never 0. So that means it has no local extrema. That doesn't mean that there's no absolute extrema. The EVT guarantees us that we have absolute extrema, but we're not guaranteed local extrema. So now we can kind of put everything all together and we can have a process to find absolute extrema. The absolute extrema of f can occur at a critical number or at the end points of closed intervals. Yes, end points of closed intervals. Look at where this absolute max occurred. It was at the end point. Where did this absolute min occur? At the end point. So absolute extrema can be at endpoints. Local extrema cannot be at endpoints. They have to have a neighborhood or an open interval around them. Absolute endpoints, okay. Local endpoints, no. Absolute extrema can be at critical numbers or at the endpoints. Okay? So now we have a process to follow to find absolute extrema for a function on a closed interval. It's the closed interval method. So here's the step-by-step process. Someone comes up to you and says, find the absolute extrema of a function on the interval from a to b. Step 1, you find the critical numbers of f on the open interval from a to b, and you evaluate the function at these points. Step 2, you also evaluate the function at the endpoints of the interval. You look at all of these function values, the largest one is going to be your absolute max, and then the smallest one is going to be the absolute min. Okay, so here we go. Find the absolute extrema of f of x on the interval from 0 to 4. So step 1, you're going to take the derivative and find the critical numbers. So f prime of x is going to be, again, I'm going to put it in descending powers whilst I differentiate. Are you cool with that? Okay, negative 12x squared plus 30x plus 18. Okay, so remember, critical numbers come from two places where the derivative is 0 and where the derivative does not exist. Now to find where the derivative is 0, let me set negative 12x squared plus 30x plus 18 equal to 0. I want to see if it's going to factor, but before I do that, I can divide everybody by negative 6, yes? Okay, so then we have 2x squared minus 5x minus 3 is 0. Factor, this is going to factor indeed 2x plus 1, x minus 3. So I get x equals negative 1/2 and x equals 3. But remember, where's my interval? Only from 0 to 4. So I'm going to throw away negative 1/2 because that's outside of my interval, okay? So right now, the only critical number of interest is x equals 3. What about where f prime of x does not exist? I get critical numbers there, but this is a polynomial. See, there's no variables in denominators, so there's not going to be any critical numbers coming from where it doesn't exist. Okay. Step 2, I want to look at what the endpoints are. So we have x equals 0 and x equals 4. And then what I like to do, I just make a table, x, f of x. And then now I put everything together from step 1 and 2. So I take my one and only critical number, and then also the endpoints, 0 and 4. And everybody goes on the table, and then you're going to find the y values. So f of 3, I did it for you already because it's so annoying. Plug it in here, okay? F of 3 is 81. F of 0, 0. F of 4, 56. And then from here you just go, oh, there's my absolute max. And there's my absolute min. Just look at the function values, the y values. Now that's a lazy little way of writing it. No, we're not going to do that. We're going to write it nicely. Absolute max, f of 3, which is 81, and absolute min, f of 0, which is 0. Good? Okay, cool. I have a couple more examples for you, believe it or not. Here we go. Find the absolute extrema of f of x equals x over x plus 1 on the interval from 1 to 2. So first thing we need to do, take the derivative. So f prime of x, it's quotient rule time again, yes? Yes. Okay. F prime of x is going to be denominator times derivative of the numerator minus numerator times derivative of the bottom over denominator squared. And then if we clean up, that's just x plus 1 minus x. So that's 1 over x plus 1 squared. Okay, so let's find our critical values or critical numbers. We want to see, where does f prime of x equal 0 and where does f prime of x not exist? Well, the derivative is 0 when the numerator is 0. That doesn't ever happen, right? None. The derivative doesn't exist when the denominator is 0. So that would mean x plus 1 squared is 0. That happens if x is negative 1. But you guys, that's not on the domain of f, nor is it inside my interval. That's not in the domain or the interval I. So it's not a critical number. So we have no critical numbers. What in the world? So all I have to go off of are the endpoints. What are the endpoints of my interval? X equals 1 and x equals 2. So we can make a table, or you could just plug them in. F of 1 is going to be 1/2. F of 2 is going to be 2/3. So one's the absolute max, one's the absolute min. Which is which? Here's my absolute max, and here's my absolute min. I'm guaranteed both by the extreme value theorem, so long as we have a closed interval on which our function is continuous. Okay, that one, aren't you disappointed a little bit? I know, I feel so sad about that one. Let's do a couple more. Find the absolute extrema of f of x equals 2x minus tangent x on the interval from 0 to pi over 3. So 0 to pi over 3, that's a closed interval. Is my function continuous on it? Well, it's a combo. It's a polynomial and a trig function. What's the domain of tangent x? We know tangent has vertical asymptotes at pi over 2, 3 pi over 2, etc. So those points all have to be removed from the domain. So the domain is all x's such that x can't equal pi over 2 plus every pi we have another asymptote, right? Every pi k, where k is an integer. But on 0 to pi over 3, we're safe because pi over 3 is smaller than pi over 2. So on this interval, we won't encounter a place where tangent's undefined. So we're good to go. We're good to go on the interval from 0 to pi over 3. Both conditions are satisfied for the extreme value theorem. So go ahead, take your derivative with a clean conscience. So f prime of x, derivative of 2x is 2, minus derivative of tangent x is secant squared x. Okay, here's my lovely little derivative. Do I have any critical numbers? I want to see where f prime of x is 0, and then where f prime of x does not exist. Okay, let me just set the derivative equal to 0. So 2 minus secant squared x equals 0. That means secant squared x is 2. Let's just rewrite that. That means cosine squared x, take the reciprocal, would be 1/2. That means cosine of x equals plus or minus square root of 1 is still 1 over square root of 2. Okay, so on the interval from 0 to pi over 3, cosine's never negative. So I'm not even going to consider cosine being negative 1 over rad 2. But cosine is positive 1 over rad 2, same as rad 2 over 2 at pi over 4, and that's within the interval. So that's a critical number right there. X equals pi over 4, okay? What about where f prime doesn't exist? Let me rewrite the derivative. It's 2 minus secant squared x is cosine squared x, right? Now this doesn't exist when cosine of x is 0. Cosine 0 when x is pi over 2, 3 pi over 2, but both those values are outside of the interval I. So I'm not going to include them. They're not relevant critical numbers for this particular problem. Only pi over 4 is, okay? And then also now we've got our endpoints. X equals 0 and x equals pi over 3. So I have 3 values that I'm going to put on my little table, x, f of x, and find the absolute min and the absolute max from amongst these. So we've got pi over 4, 0, and pi over 3. Okay, very good. So let's see here. F of pi over 4 is pi over 2 minus 1, which is about 0.57. F of 0 is 0. And f of pi over 3 is 2 pi over 3 minus rad 3, which is about 0.36. So from here, this guy is my absolute min, and this one's the absolute max. So we can write it nicely. F of 0 equals 0, that's the absolute min. and then f of pi over 4, which is pi over 2 minus 1, is the absolute max. Good? Okay. Last one, we're going to do a piecewise function. All right, last example, sketch the graph of the function and then just use your sketch to find the local and absolute extreme values of f. So we don't need to go through the process of taking derivatives and whatnot. So f of x equals 4 minus x squared if x is greater than or equal to -2 and less than 1. And then f of x is 2x minus 1 if x is greater than or equal to 1 and less than or equal to 3. Okay, if you actually need help graphing piecewise functions, I have a video showing you a process that'll make you a professional. And then once you're a professional, you can probably ditch the process, like take your training wheels off, you know, and just graph it by looking. So I'm, observing here the x values go from -2 to 3. All right, and then 4 minus x squared, I know that's a parabola opening downward, and then this is going to be a line. Good? Okay, -1, -2, 1, 2, 3. And then let's see, I don't think I'm going to have to go too much higher than 5. 1, let me make it really spread out. 1, 2, 3, 4, 5. Ooh, I love it. Okay, I'm going to start plugging in. -2. 4 minus -2 squared, that's 4 minus 4. That's going to be 0. If I plug in -1, that's going to be 4 minus 1. That's 3. 1, 2, 3. And then I know at 0, it's 4. Then it's going to come back down. But here at 1, when x is actually equal to 1, I'm going to plot an open circle. Because notice this inequality is strictly less than 1, not less than or equal to 1. So you still take 1, plug it in here. 4 minus 1 is 3, but plot it with the open circle. So here's this piece here. Ah! Came out wobbly on the other side. Hold on. Hold on. Oh, yes. Now I'm proud of it. Okay. Then the next part, hopefully this is relaxing. It's just a sweet little line. See how this inequality is inclusive? So I'll have a closed circle. 1, when I plug in 1 for x. 2 times 1 minus 1 is 1. So we've got 1, 1. Then 2, that's 4 minus 1, that's 3. Okay, and then 3, 5. Boom. And it stops there, so don't put an arrow. Perfect. Wow, look at us. We need to find, look how demanding, local and absolute extreme values. Okay, so local max, local min, absolute max, absolute min. Okay, local max, do we have any? Yes, 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 right here. F of 0, which is 4. That's a local max. F of 0, which is 4. You guys, can this be a local max? No, because it's an endpoint. Remember, local means there's a neighborhood around it, that there's an open interval. Values to the left, values to the right. There's no neighborhood on this side. So sorry, you can't be a local max. Is there a local min? This one is so funky. Yes, this is a local min. I know. You're like, where's the neighborhood? It's right here. So there's values to the left and values to the right. And this is the smallest in that neighborhood. We're not looking at this neighborhood over here, even though that technically makes it a local min. This one's always weird when the graph breaks like that, okay? But it is technically a local min. So f of 1, which equals 1, is a local min. I know that one would always make me upset when I was a student. Absolute max, do we have one? Yes, right here. This is our absolute max. Not this one, because this function value is larger. So my absolute max is f of 3, which is 5. And absolute min, do I have one? Yes, right here. Not this one, because this function value is smaller. F of -2, which is 0. All right, good. That's it. That's it. That's it. I wanted to show you one more example to drive home the criteria of the extreme value theorem. Okay. And this is just so you kind of appreciate the statement of it. I want you to consider, but technically the lesson's done, you know? I want you to consider f of x, which equals 4 minus x squared. Do you guys know what that looks like? Parabola, right? Opening downward. Y-intercept is 0, 4. X-intercept's plus or minus 2. Okay, let's graph it. 1, 2, 3, 4. 1, 2. 1, 2. 0, 4, 2, 0, -2, 0. Here it is. Extreme value theorem tells me I have absolute extrema as long as we have closed interval on which the function is continuous. Now it's continuous everywhere because this is a polynomial, so it's continuous on all real numbers. At the moment, if I consider the entire domain, from -infinity to infinity, I have an absolute max right here, f of 0, which is 4. Do I have an absolute min? No, no absolute min. Why is that? Because I don't have a closed interval. Now, if I just only consider a piece of this graph, only consider whatever piece you want, maybe from -1 to 2. So if I'm only looking from -1 to 2, I'm only looking at the piece of the graph between -1 and 2. So I'm looking at this piece here. Now do I have both? Yeah. I still have my absolute max. Where did that happen? Same place, f of 0, which is 4. But now I also have an absolute min right here. Absolute min, where is it? F of 2, which is 0. This happened at the end point. The absolute max happened where the derivative is 0. That's a critical number. Critical number. Critical number. So that's why, remember the process that I showed you when you're finding absolute extrema? When you have a continuous function on a closed interval, you have to look at all the critical numbers and the endpoints, and from there you'll find your absolute min and your absolute max, because both are necessary. This endpoint here is not a critical number, right? But it is my absolute min on this particular interval. Now, if I change the interval, if I went from -1 to 3, I'd have a different absolute min, but I'd still have an absolute min. And that's the crux. That's what that extreme value theorem is telling us, okay? So this is a lot. The actual process of finding absolute extrema, pretty straightforward, pretty short. You could probably explain it to your friend. There's so much going on behind the scenes, and we're going to build on this, okay? So make sure you stay tuned, have your notifications on, subscribe. And I have a different series of video lectures on Calc 1 already published, so if you just don't want to wait for me to release the new videos, you can go watch those. I'll link them all here, the Calculus 1 video lectures playlist. Leave a comment down below. Let me know what your favorite function was that we played around with in this video. And I'll be back sooner than later with more content for you guys, all right? Thanks so much for your support. Love you all. Follow me on Instagram and TikTok, Math with Professor V. Bye, guys.